Leah here from Leah4sci.com, and in this video we'll continue our SN2 discussion by analyzing a number of SN2 reactions and their mechanisms. We'll start with a chiral 2-iodobutane reacting with NaSCH3 in the presence of acetone. But first let's determine that an SN2 reaction can take place by analyzing the alkyl chain leaving group attacking nucleophile and solvent. You can find detailed videos showing you what to look for in each of these scenarios by visiting my website, Leah4sci.com/substitution-elimination. So let's begin. We have a leaving group sitting on a secondary carbon, which tells me that in the case of an SN1 reaction, I can have a stable carbocation, but in the case of an SN2 reaction, I don't have enough steric hindrance to prevent a nucleophile from attacking directly, and this tells me that I can have a 1-type and a 2-type reaction take place based on the alkyl chain. Iodine is a decent leaving group, so we can have a 1-type and a 2-type reaction. Our attacking molecule is where it gets a little tricky. Recall that in an SN1 reaction, you typically have a weak nucleophile, and because it's not strong enough to attack, it waits for the leaving group to leave and then swoops in on the carbocation. In this case, it appears that we have a neutral or weak attacking molecule, but that's actually not the case. Anytime you see Na or some other group 1 metal at the start of your molecule, recognize it as a positive spectator ion secretly hiding a negative charged atom or molecule. And in this case, we have a negative sulfur, which is charged and therefore strong enough to initiate an attack, meaning a 2-type reaction. But we'll take this further than just a blanket 2, which can include SN2 or E2. Sulfur, which sits directly under oxygen on the periodic table, is a larger atom with its charge distributed. This makes it a weak base because the charge isn't as concentrated or strong. However, because the sulfur is so large, the atom is polarizable, and when you can polarize your attacking molecule, it tends to form a better nucleophile. So in addition to writing 2, we'll say that SN2 is favored over something like E2, meaning it's pointing towards an SN2 reaction. And lastly, we'll analyze our solvent, which is acetone, or simply propanone. Notice that it's a polar aprotic solvent, polar because we have the carbonyl oxygen hogging electron density towards itself and the partially positive carbonyl carbon. But the hydrogens on this molecule are located on carbons and therefore are not polar enough to participate in hydrogen bonding. Since acetone doesn't have the capability of hydrogen bonding our nucleophile, it tends to be more reactive in this solution and therefore more likely to attack. And polar aprotic solvents tend to favor the SN2 reaction. And so the clues justify that an SN2 reaction can take place. Let's redraw the starting molecule and show the reaction. One more time. I'm going to twist the starting molecule before looking at the reaction because I want to emphasize what happens to the leaving group when the molecule gets attacked. Iodine is an electronegative atom, and even though it's covalently bound to carbon, will pull electron density towards itself, giving it a partial negative charge. This makes the attached carbon partially positive. We'll show the nucleophilic portion of our attacking molecule, which is a CH3S with a negative charge, and this negative sulfur will polarize all its negativity towards the direction of the carbon atom to the point where it's actually attracted enough to form a bond between itself and carbon. When sulfur attacks, it creates a 5th bond to carbon, but carbon can only have 4 bonds, so iodine is forced to take its bonding electrons and break away from the molecule. Now the key part of this reaction is paying attention to what happens in the intermediate step. We'll show the invisible hydrogen to make the intermediate make a little more sense. We'll show the central carbon so you get a better understanding of what goes on with the hybridization and the way the atoms are attached. At the top of the molecule we have a CH3 group. It starts out facing left, but as the sulfur comes in and attacks, it gets pushed slightly to the right, and so the CH3 group in the transition state is pointing straight up. The hydrogen, which was down and towards the back, is still going to stay where it is, and the 2-carbon chain towards the left is going to come slightly forward. The CH3S is partially attached during the transition state, and at the same time, the iodine leaving group has partly broken away. So notice that we had a molecule that started out chiral, sort of straighten out in the middle, meaning the carbon has the substituents facing straight up and down, but you have the leaving group and the nucleophile attached. So this means that your chirality in product is going to be controlled in terms of how it winds up. We'll put brackets around the transition state because this is not something you have to show when working through the reaction. Instead, I want you to understand what's happening. And finally, to complete this reaction, the bond between carbon and sulfur will get stronger. The bond between iodine and carbon will completely break. And as this happens, everything attached to carbon will be slightly pushed over to the other side to make room for that incoming nucleophile. Let's quickly verify the stereochemistry of the starting and the ending molecule. In the starting molecule, iodine is my highest priority, then ethyl, then methyl, and I already have hydrogen towards the back. Tracing from 1 to 2 to 3, I get an R configuration for my starting molecule. I do the same thing to my product where the SCH3 is priority 1, ethyl is 2, methyl 3, hydrogen 4 is already in the back, so we ignore that. And once again, we trace from 1 to 2 to 3, in this case going counterclockwise and giving me the S configuration. As you can see, we started out with a pure R enantiomer, and after undergoing an SN2 reaction, we wound up with a pure S enantiomer, given that the SN2 reaction involves an inversion of configuration. The final thing we want to verify in any reaction is the conservation of charge. We showed the starting molecule as NaSCH3, which was neutral. Here we're showing it as S-. It doesn't matter which one you use as long as you're consistent. If we use just the S-, then we can say the reactants have a net charge of -1. The product appears to be neutral, but don't forget that we had an I- break off in solution. That I- has a negative charge, giving the product a net charge of -1. Now that we understand how the SN2 reaction takes place, I want to show you a quicker way to draw this because the transition I used above is kind of tricky and will get messy on your exam paper. Given that these are our reacting molecules, we can show a lone pair of electrons on sulfur attack from the opposite side of iodine. But understand that because iodine is drawn with a wedge, it's coming out of the paper. And even though we're showing sulfur attack from the top, it's attacking from the opposite side of iodine. In other words, it's attacking from beneath the molecule or beneath the paper. When we show the product, we keep everything the same except for the leaving group and the incoming group, which switch places. To show that sulfur is beneath the paper, we draw the bond between carbon and sulfur as dashes and then simply add SCH3. On paper, it looks like the chirality inverted, but let's quickly prove that by finding the stereochemistry of the reactant and product. The product appears to be R, but because hydrogen is forward and group number 1 is in the back, R actually becomes S because we envision this backwards. And lo and behold, an R molecule undergoes an SN2 reaction and gives me an S product. In this example, we'll analyze what happens when a primary chlorine on a substituted cyclopentane is attacked by a strange molecule LiCCCH3. Let's prepare our checklist and see what we can make of this set of conditions. Our alkyl chain has a leaving group on a primary carbon, which means we cannot form a stable carbocation, and since the SN1 and E1 reaction undergo a carbocation intermediate, we're ruling out the 1 type, leaving us with the 2 type reactions, SN2 and E2. Chlorine is an okay leaving group, which means that it can be kicked out in a reaction, and therefore a substitution or elimination can take place. Then we have our strange attacking molecule. At first glance, it doesn't appear to be a molecule that I recognize, but if you analyze the atoms carefully, you can actually make sense of it. Li at the start of a molecule is very likely a positive spectator ion, meaning I have a negative charge on the attached molecule. The fact that a molecule is negative means it's a strong attacker and will prefer a 2 type reaction, meaning SN2 or E2. If we then draw out the nucleophile to see the bonds carefully, notice we have a methyl group on one end of the molecule, a negative charge on the other end, but we don't have any hydrogens on those first 2 carbons, and this tells me that I have to have a triple bond between them. Now we have a molecule that we recognize. An sp carbon with a negative charge is a highly polarizable molecule due to the pi bonds, and this makes it an okay base, but a very good nucleophile. The fact that our molecule is a better nucleophile than it is a base, we're going to have the SN2 reaction preferred over the E2 reaction. And lastly, we have DMSO, which is dimethyl sulfoxide. This is a polar aprotic solvent, which means it doesn't really stabilize any charged intermediates. Anything charged in solution will be considered stronger by default, and this tends to favor an SN2 reaction. Analyzing all the clues together, an SN2 reaction can indeed take place. We'll redraw the molecules so that we can show the mechanism, and we'll only focus on the negative portion of our attacker. Chlorine as a halogen draws electron towards itself, giving it a partially negative charge, causing the attached carbon to become partially positive. Our nucleophile is attracted to this partially positive carbon, attacking with a lone pair of electrons and forming a bond between itself and the carbon holding the leaving group. This causes chlorine to grab the electrons that attach it to carbon and break away into solution. This one-step reaction results in a much larger chain where I first had my primary carbon. Notice that we didn't talk about stereochemistry in this reaction, and that's because chlorine was not on a chiral molecule to begin with. Let's not forget that the primary carbon had 2 invisible hydrogen atoms, and the criteria for a chiral carbon is 4 unique substituents, which means that we didn't have a chiral starting product, nor do we have a chiral ending product. Be sure to join me in part 3 of the SN2 series, where I show you how to do a reaction with a leaving group that doesn't want to leave. Are you struggling with organic chemistry? Are you looking for information to guide you through the course and help you succeed? If so, download my ebook, 10 Secrets to Acing Organic Chemistry, using the link below, or visit Leah4sci.com/orgosecrets. That's ORGO secrets. For information regarding online tutoring, visit Leah4sci.com/orgotutor. That's ORGO tutor. If you enjoyed this video, please give it a thumbs up and even share it with a friend or two. If you have any questions regarding this video, leave a comment below or contact me through my Facebook page at facebook.com/Leah4sci. There will be many related videos posted over the course of the semester, so go ahead and click the subscribe button to ensure that you don't miss out.